Picture, if you will, a quiet blue world turning slowly in the dark, long before any footprint marked its shores. Before we go any further, if you want a brand new Earth topic every single night to fall asleep to, subscribe. One tap and a new story is waiting for you every evening. This is the Earth, but not the Earth you know. There are no green continents shaped the way you remember them from maps. There are no familiar coastlines. There are no great beasts walking the plains. No birds drifting on warm winds. No whales rolling through the deep. There is only water and stone and sky and time. For most of our planet's long life, this was the way of things. The dinosaurs, who feel so impossibly ancient to us, are actually quite recent visitors. They arrived only in the last quarter of Earth's story. Behind them stretches an enormous quiet, billions of years of slow change, of strange chemistry, of soft and nameless creatures drifting through warm seas. That long quiet is what this episode is about. And the deeper we look into it, the more we find that we do not really understand it at all. Imagine drifting high above the planet, looking down. The continents below are not in their familiar places. They slide and gather and break apart over hundreds of millions of years, like slow ships on a sea of hot rock. Sometimes they crash together into one great landmass. Sometimes they scatter into pieces. The oceans between them rise and fall. Ice creeps down from the poles, then melts back again. Whole mountain ranges grow and crumble to dust. And all of this happens before a single dinosaur ever opens its eyes. We know some of this story from the rocks. Layers of stone, stacked one on top of the other, hold the faint records of ages we will never see. A line of red iron here, a band of black shale there, a thin smear of crushed shells, no thicker than a finger, that took 10,000 years to gather. The Earth is, in a sense, its own slow library, but the pages are torn, and many of them are missing. And the older the page, the harder it is to read. This is the heart of the mystery we will sit with tonight. What was the Earth really like in those long ages before the dinosaurs? Some researchers believe the early planet was a warm, gentle place for most of its history, with shallow seas full of soft, strange life. Others suspect it swung between terrible extremes, frozen nearly solid for millions of years at a stretch, then thawing into hot, steamy worlds we would barely recognize. The evidence supports parts of both ideas. The full picture remains open. There are whole chapters of life we know almost nothing about. We have found impressions in stone of creatures with no clear relatives today. Soft shapes that look like quilted leaves or ribbed discs lying on an ancient seafloor. No one is sure what they were. Some scientists think they were early animals. Others think they were something else entirely, a separate experiment in living that simply did not last. The fossils do not tell us. They only hint, and there are gaps, long, silent gaps where the rocks have been worn away, or buried too deep, or pressed and twisted until any fossils inside them were erased. We have only fragments of the deep past. We are reading a book where most of the pages have been lost to wind and water, and the slow grinding of the continents themselves. Yet from these fragments, something wonderful emerges. The Earth before the dinosaurs was not a lifeless place waiting for the real story to begin. It was alive in its own quiet ways. Mats of tiny organisms built domes on warm shorelines. Jawless fish slipped through dark waters. Forests of strange, tall plants rose where no forest had ever stood. Insects grew to sizes that would astonish us. Whole worlds came and went, and most of them have no name in any language ever spoken. Tonight, as you settle in, we are going to drift slowly through that long, quiet age. We will visit warm, shallow seas and silent stone shores. We will wonder about creatures whose shapes we can barely guess at, and about climates we can only sketch in soft outlines. We will not solve the mystery. The mystery is too old and too large and too gently buried for that. But we can sit with it together and let the long silence of the deep past settle around us like a soft, dark blanket, while the world outside your window goes quietly on. To picture the world before the dinosaurs, we need to set aside almost everything that feels familiar about life on Earth. No grass, no flowers, no bird song drifting through trees, no trees even for most of the story. For the longest stretch of Earth's history, surface of our planet held nothing you could call an animal at all. The seas were warm and quiet. The land was bare rock and dust, and the living things that did exist were so small, so soft, that they left almost nothing behind. Earth itself is about 4.5 billion years old. That number is hard to feel, so let's slow it down. If you imagined the whole history of Earth as a single calendar year, with the planet forming on January 1st, then the dinosaurs would not appear until the middle of December. Humans would arrive in the final minutes of December 31st. Everything we are about to wonder about in this episode happened in the long, slow months before that late December arrival. The story stretches back through autumn, summer, spring, and deep into the empty winter at the start of the year. For most of that time, Earth had no bones in it. Bones are a fairly late invention, so are shells, teeth, claws, and wood. These are the hard parts that fossilize well. They are the parts that leave clear marks in stone. Without them, the record of early life is faint, like footprints in shallow water that almost wash away. This is one reason the deep past stays so mysterious. We are not looking at a complete picture. We are looking at scattered hints pressed into ancient rock. The earliest signs of life go back at least 3.5 billion years, and possibly further. These signs are not creatures. They are chemical traces and layered mounds called stromatolites, domes built by mats of tiny, single-celled organisms. Stromatolites look a bit like stacked stone pillows, rising in shallow water. A few still grow today in salty bays in Australia, and they look almost exactly like their ancient cousins. For more than 2 billion years, that was life on Earth. Mats, slime, single cells drifting in warm seas. It is hard to overstate how long this quiet phase lasted. If you took the time between the first stromatolites and the first true animals and laid it end to end, it would be longer than all the time that has passed since animals first appeared. The age of microbes was the main act. Everything we usually think of as life, fish, insects, ferns, lizards, mammals, fits into a much shorter final chapter. Then, somewhere around 600 million years ago, things began to change. Soft, Strange shapes appeared in the shallow seas. Some looked like quilted pillows. Some looked like fronds anchored to the seafloor. Some looked like flat discs with faint ribs. We call them the Ediacaran biota, after the hills in southern Australia where they were first studied closely. They had no shells, no skeletons, no obvious heads or tails. Whether they were early animals, early something else entirely, or a failed experiment in life's design, the question is still open. Some researchers think they are the ancestors of later creatures. Others wonder if they were a separate branch that simply faded out, leaving no descendants at all. After the Ediacarans came what is often called the Cambrian explosion, about 540 million years ago. In a relatively short stretch of geological time, hard parts appeared: shells, spines, compound eyes, the first true predators with grasping limbs. The seas filled with strange swimmers and crawlers, many of them looking like nothing alive today. We will sit with this puzzle in a later section, because the speed and cause of that bloom are still debated. For now, hold the simple shape of it in your mind. A planet about 4.5 billion years old. Life, for most of that time, was microscopic. Soft creatures came late. Hard creatures came later still. Dinosaurs, which feel so ancient to us, are actually newcomers in this long story. They arrived more than 3.5 billion years after the first stirrings of life. The world before the dinosaurs was not one world. It was many. Continents drifted into different shapes. Oceans opened and closed. Ice came and went. Skies shifted in color as the air itself changed. The land was sometimes red, sometimes gray, sometimes draped in pale green mats near the water's edge. We are about to walk slowly through these changing scenes, knowing that much of what we say will be partly guesswork. The deep past keeps most of its secrets. We only catch glimpses, pressed faintly into stone. Picture an Earth that is almost a stranger to us. The sky is not blue, but a soft, hazy orange, thick with gases we would find hard to breathe. The seas are not the rich green and deep sapphire we know today. They are tinted with iron and other minerals, sometimes the color of rust, sometimes the color of weak tea. The land is bare. No grass, no trees, no soil in the way we picture it. Just stone, sand, and the slow drift of dust under a young sun. This is the world where the first stirrings of life began. And the strange truth is that we still do not fully know how it happened. The Earth itself had already been around for nearly 1 billion years before anything we might call living seemed to appear. In those long, quiet ages, the planet was busy in its own way. Volcanoes pushed up new crust. Comets and asteroids still rained down from time to time, though less often than before. The oceans were warm in some places, scalding in others. Steam rose from cracks in the seafloor where hot water met cold. It is in those cracks, some researchers think, that life may have begun. These are called hydrothermal vents, chimneys of mineral rock that grow up from the deep ocean floor, pouring out heated water rich in chemicals. In the dark, with no sunlight at all, the chemistry of these vents could have built the first simple molecules of life. Some scientists believe the gentle, steady warmth and the strange brew of minerals gave nature its first kitchen. But this is only one idea. Another theory points instead to shallow, sunlit pools at the edges of the early continents. In these warm little ponds, water would evaporate and refill, evaporate and refill, slowly concentrating the chemicals dissolved within. Lightning may have flashed above. Ultraviolet light streamed down through the thin, strange sky. In such a setting, the building blocks of life might have linked together on the dry rim of a drying pool. We do not know which picture is closer to the truth. Both may hold a piece of it. Both may be wrong. What we do find, written in stone, are the oldest hints of living things. They come in the form of stromatolites, layered mounds built by mats of tiny single-celled creatures called microbes. These mounds look like rounded cushions of rock, stacked in soft, wavy layers. The microbes themselves left no skeletons, no shells. They left only the patterns of their slow growth, mineral upon mineral, season upon season. Some stromatolite fossils are more than 3 billion years old. They are among the oldest signs of life we have ever found. Try to imagine the scene. A shallow sea under a pale, hazy sky. Tides lapping gently against low, dark rocks. Beneath the water, soft green and purple films coat every surface. There are no fish, no crabs, no waving fronds of seaweed. There is no sound but the wash of small waves. And yet life is there, quietly working, slowly changing the chemistry of the entire planet. The first stirrings of biology were not loud. They were patient beyond our understanding. How those microbes first arose is the deeper mystery. Some scientists wonder if the basic molecules of life formed here on Earth from local ingredients alone. Others suggest those molecules, or hints of them, might have arrived on the dust of meteorites, sprinkled into the young seas from far away. The chemistry of certain meteorites does carry simple organic compounds. Whether those compounds matter to our own origin remains an open question. What we can say is that the conditions had to be unusually steady. Liquid water needed to stay liquid for a long, long time. The planet needed to hold on to enough warmth without becoming a furnace. The early atmosphere needed just the right balance of gases. None of these things were guaranteed. Many young planets, we suspect, never reach this point. Earth did. We are still trying to understand why. For most of this early chapter, the story moved in slow motion. Hundreds of millions of years passed with microbes as the only residents. The seas changed color slowly. The skies shifted in hue. The continents drifted, broke, and rejoined in patterns we can only partly reconstruct. These first stirrings set the stage for everything that came after. The bones, the forests, the giants. They began here in the warm and quiet seas of a younger world, in a beginning we may never fully see. For tonight, we can only sit beside that ancient water and wonder. For the longest stretch of Earth's history, the oceans could not breathe. There was no free oxygen in the water, and almost none in the air above it. The sky may have looked pale orange, or hazy gray, or some color we cannot quite imagine from where we stand now. The seas were a strange chemical broth, rich in iron, poor in the gas that all complex life would one day need. And then, very slowly, something began to change. The change came from the smallest possible source. Tiny single cells drifting in shallow water, learned a trick that would remake the world. They learned to take sunlight and split water molecules apart, keeping the hydrogen and releasing the oxygen as a kind of waste. We call these cells cyanobacteria, though that name is just a label we placed on a lineage far older than any animal. For perhaps 2 billion years, they quietly exhaled into the sea. At first, the oxygen had nowhere to go. The oceans were full of dissolved iron, and oxygen binds to iron eagerly. The two combined again and again, and rusted out of the water in great red drifts that settled to the seafloor. Today we find these layers as banded iron formations, striped bands of rust and dark rock pressed into cliffs in Australia, Canada, and South Africa. Much of the iron we mine for steel comes from this ancient rusting of the seas. Every skyscraper, every bridge, every iron nail carries the chemistry of a planet learning, for the first time, how to breathe. Only after the oceans had rusted through did the leftover oxygen begin to drift upward into the air. This shift is called the Great Oxidation Event, and we still argue about how fast it happened and why it happened when it did. Some researchers think a slow shift in the planet's volcanoes allowed oxygen to build up. Others wonder if the early continents themselves changed shape, exposing fresh rock that locked away the gases that had been smothering oxygen for ages. The question remains open, and the truth is likely a tangle of causes we have not yet untangled. It helps, sometimes, to remember where all of this material came from in the first place. The iron in those rusted seafloors did not begin on Earth. It was forged in the cores of dying stars, scattered across space in long-ago explosions, and gathered together when our planet first pulled itself into a ball of molten rock. The same is true of the calcium that would one day build shells and bones, the carbon that would build every living cell, the silicon in every grain of sand on every beach. Earth is, in a real sense, made of star leftovers. Even the water is a mystery. Some of it likely came from the rocks themselves, sweated out by volcanoes over hundreds of millions of years. Some of it may have arrived from the outer edges of the young solar system, locked inside icy comets and water-rich asteroids that struck the early Earth we do not know the exact mix. One idea is that most of our oceans came from within. Another is that a large fraction was delivered from far away. Researchers compare the chemistry of comet ice to ocean water, looking for matches, and the answers so far are partial. The atmosphere shifted alongside the seas. Early air was thick with carbon dioxide, methane, nitrogen, and water vapor. As oxygen rose, methane fell, and the planet may have lost a warm blanket it had relied on for billions of years. Some scientists think this thinning of methane helped trigger the first great glaciations, the long, deep freezes, sometimes called Snowball Earth. Others believe the freezes came from changes in how continents weathered, pulling carbon dioxide out of the air faster than volcanoes could replace it. Both ideas are still discussed. The evidence is locked in old stones, and old stones speak softly. What stands out from this great distance is how connected everything was. The breath of a microbe in a shallow lagoon rusted the iron of the sea. The rusted iron later became steel in distant cities. The collapse of methane in the sky froze the oceans. The frozen oceans set the stage for the strange, soft creatures that would come next. Each link is small. Together, they form a chain that runs from a dying star, through a comet, through a cell, through a stripe of red rock, all the way to your bedroom window tonight. We are still learning to read this chain. Much of it is faint, smudged by time. The oceans learned to breathe long before anyone was there to notice, and the planet has been quietly remembering ever since. Long before anything walked, before anything swam with bones or bit with teeth, the seas of Earth held a strange and quiet garden. We call it the Ediacaran world, and it bloomed across the ocean floors more than 550 million years ago. The creatures of this time had no shells, no skeletons, no jaws, no claws. They were soft, they were slow, and many of them looked like nothing alive today. Some were shaped like fronds, anchored to the seabed by a small bulb. They swayed in the slow currents like quilted leaves. Others were flat ovals, ribbed and pillowy, resting on the mud like fallen pancakes. A few were shaped like tiny discs, or three-pointed stars, or long segmented ribbons. colors are lost to us. We can only guess at the soft pinks, pale browns, and ghostly whites that might have drifted in that ancient light. What forces shaped this strange bloom of soft bodies? That is one of the deepest questions in the study of early life. The answer seems to lie in a handful of slow, patient pressures working together across many millions of years. The first was oxygen. As we have already wondered, the seas had been slowly learning to breathe. By the late Ediacaran, oxygen levels in the shallow oceans appear to have risen enough to support larger, more complex bodies. A creature the size of your hand needs more oxygen than a single cell. Without that gentle rise in breathable water, the soft fronds and quilted discs could never have grown so wide. The second force was gravity itself, working in a strange way. On land, gravity pulls heavily on anything tall. But in the sea, water holds a body up. A soft frond can stand many times taller than it could on dry ground, because the water cradles its weight. The Ediacaran creatures took advantage of this. Some grew nearly a meter long without a single bone inside them. They were sculptures of jelly and tissue, held upright only by the press of the sea. The third force was pressure, slow and steady, from the water above. In the calm depths, pressure is gentle but constant. It shapes soft bodies into smooth, rounded forms. The quilted patterns we see in Ediacaran fossils may be the marks of internal chambers, each one inflated against the weight of the ocean. Some researchers think these chambers held fluid. Others think they held nothing at all and were simply folds of living tissue. The question is still open. Then there were the tides. The moon was closer to Earth in those days, and the tides may have been stronger. Long, slow pulses of water washed across the shallow seabeds where these creatures lived. Some of them may have fed by simply absorbing nutrients from the moving water, drinking it in through their soft skin. Without mouths, without guts, they lived by surface alone. One theory suggests they were a kind of living filter, taking in sugars and minerals from the sea like a sponge soaks up rain. Sunlight, too, may have played a part. In the shallow lagoons, light reached the seabed easily. Some scientists wonder whether certain Ediacaran creatures hosted tiny photosynthetic partners inside their tissue, the way some corals do today. Others think they were entirely independent of sunlight, feeding only on the microbial mats that carpeted the floor. We do not know which idea is closer to the truth. Both leave fingerprints in the fossil record. Neither has been proven. And there were the microbial mats themselves, thick, slimy carpets of bacteria coated the seabed in those days. Before burrowing animals existed to churn the mud. The Ediacaran creatures lived directly on these mats, and many seem to have fed on them. The mats held the seabed still. They preserved the soft impressions of bodies that would otherwise have rotted away without a trace. Without those quiet bacterial gardens, we might have no fossils of this age at all. What we are left with is a picture of a world held together by gentle forces. Soft, oxygen-rich water, buoyant pressure, slow tides, stable microbial floors. Each one was needed. Remove any of them, and the strange bloom might never have happened. And yet, after tens of millions of years, the Ediacaran creatures vanished. No one knows exactly why. Some researchers think rising oxygen finally allowed predators to evolve, and the soft fronds were simply eaten. Others suspect the microbial mats themselves were destroyed by new burrowing animals churning the mud. A few wonder whether the chemistry of the sea shifted in some quieter way we have not yet detected. The garden faded. What replaced it would be Strand. About 540 million years ago, something strange began to happen in the shallow seas. After billions of years of soft, simple life, the oceans filled with creatures that had eyes, shells, legs, and jaws. We call this burst of new forms the Cambrian explosion. And to feel its scale, it helps to slow down and stretch the numbers out until they sit in the body and not just the mind. Imagine the whole history of Earth as a single calendar year. Earth forms on January 1st. Simple cells appear in February or March. For most of the year, life stays small and soft. The first stromatolite mats, those layered cushions of bacteria, spread through the seas in spring and summer. By autumn, the planet has plants of a sort, but no animals you could hold in your hand. The Cambrian explosion in this calendar begins around the middle of November. The dinosaurs do not show up until mid-December. Humans appear in the last half hour of December 31st. The Cambrian, in other words, takes up only a few weeks of Earth's vast year. And yet, in that short slice, the basic body plans of nearly every animal alive today appear. Stretch the timeline another way. If you laid out 4.5 billion years of Earth history along a single mile of quiet road, each step you took would cover about 1,000 years of human history. You would walk and walk through a long, dim age of microbes. Then, somewhere in the last 150 feet of that mile, the Cambrian seas would bloom with trilobites and odd swimmers. The dinosaurs would rise and fall in the last 40 feet. You and everyone you have ever known would fit inside the final inch. The creatures themselves are small by our standards, and that is part of the wonder. Most Cambrian animals were the size of a fingernail, a paperclip, a grape. A common trilobite might fit in the palm of your hand, no bigger than a wristwatch. The famous Anomalocaris, often called a giant of its age, was about the length of a loaf of bread. By the measure of later seas, with their whales and great sharks, the Cambrian world was a quiet miniature. A child wading in those shallows would have towered over every living thing. And the seas themselves were warmer than ours and shallower in many places. The continents looked nothing like the maps we know. Most of the land sat far from where it sits today, drifting in clusters near the equator and the south. Sea levels were high. Wide, sunlit shelves covered places that are now dry interior plains. If you could stand on one of those Cambrian beaches, the horizon would feel familiar. Pale sky, gentle waves, but no birds, no crabs scuttling, no seaweed swaying in the way we know. Only the soft sound of water on bare stone and life unseen beneath the surface. The puzzle is the speed. In the long calendar of Earth, the burst of new body plans took perhaps 20 or 30 million years. That sounds slow to us, but against the 3 billion years of soft, simple life that came before, it is a sudden flowering. One theory holds that oxygen finally rose to a level that allowed bigger, hungrier animals to thrive. predators and prey pushed each other into shells, eyes, and faster swimming. Another idea suggests that the genes for complex bodies had been quietly assembling for ages and only needed the right conditions to switch on. A third view wonders whether the explosion is partly an illusion of the rocks themselves. Hard shells fossilize well. Soft bodies rarely do. Perhaps the change was less sudden than the stones make it seem. We do not yet know which of these stories holds the most truth, or whether the real answer is a quiet blend of all three. The fossil record from before the Cambrian is thin, like a book, with most of its pages torn out. What we have are scattered chapters in places like the Burgess Shale in Canada, the Chengjiang beds in southern China, and a handful of sites in Greenland and Australia. Each window is small. Each one shows a different angle of a world we can only partly imagine. Hold the scale for a moment. 3 billion years of stillness. A few million years of sudden invention. Then 500 million more years of branching life, leading slowly to the creature listening to this voice. The Cambrian sits in the middle of that long story, like a single bright bead on a very long thread, still glinting with questions we have not yet learned how to ask. Imagine drifting just above a shallow sea, somewhere near the end of the Cambrian, around 500 million years ago. The water is warm, warmer than most seas today, and the sun filters down through it in soft green and gold ribbons. The sky above is pale, almost milky, because the air still holds less oxygen than the air we breathe now. There are no gulls calling. There are no fish leaping. There is only the gentle hush of waves moving across a world that has not yet learned the sound of bone. Below you, the seafloor stretches out in pale shades of cream and rust. Wide carpets of microbial mat coat the sand, glistening like wet silk. Around them rise the first true reefs of the early Paleozoic, built not by corals as we know them, but by strange sponge-like animals called archaeocyaths. They look a little like nested ice cream cones, with double walls full of small windows, and they cluster together in pale mounds the color of bone and honey. Between these mounds, the sand shimmers with fine grains of quartz and tiny shell fragments, soft as powder. If If you let your eyes rest on the reef, you begin to see movement. Long, segmented creatures glide just above the seafloor, their bodies armored in dark, glossy plates. These are the trilobites, and in this age they are everywhere. Some are the size of a thumbnail. Some are as long as a forearm. Their shells come in countless shapes: smooth ovals, ribbed crescents, fans studded with delicate spines. Their colors are still debated, but many likely wore mottled browns, deep coppers, and quiet greens, the better to vanish against the muddy floor. A trilobite passes beneath you, its many small legs moving in soft, rippling waves under its shell. Its compound eyes, made of tiny calcite crystals, catch the light and shine like wet beads of glass. These were among the first true eyes on Earth, and we still wonder how sharply they saw. One idea is that they perceived a clear, mosaic image of their world. Another is that they registered only motion and shadow. The fossils preserve the lenses, but not the seeing. Above the trilobites, in the open water, glide creatures stranger still. Long, slender shapes drift by inside cone-shaped shells, their tentacles trailing behind them. These are early nautiloids, distant cousins of today's squid and octopus, and some of them grow longer than a person is tall. Their shells are banded in pale and dark stripes, the colors of weathered ivory and tea. They hunt slowly, drifting on subtle jets of water, their soft arms feeling along the reef for anything small enough to grasp. Nearer the surface, small, jawless fish-like animals swim in loose schools. They have no fins as we picture them, only ribbon-like tails that beat from side to side. They look almost shy in this world of armored giants, soft and silvery against the green light. They are quiet ancestors, and the oceans will one day belong to their descendants. For now, they are only minor figures in a kingdom of shells. If you drift closer to the reef itself, you find smaller wonders. Tiny brachiopods, shaped like little stone hearts, cling to the Archeosiath walls by thin stalks. Sea lilies, called crinoids, sway on long jointed stems, their feathery arms opening like pale flowers to catch passing scraps of food. Worm-like creatures peek from holes in the sediment, their fringed mouths blooming and closing in the current. everything is moving, but slowly, as if the entire reef is breathing in one long, patient rhythm. What remains uncertain is how these reefs truly sounded, smelled, and shifted through the seasons. The fossils preserve the shapes and the chemistry, but they do not preserve the small daily life. Some researchers picture these seas as crowded, noisy, with the clicks and rustles of countless small animals. Others picture them as nearly silent, broken only by the wash of waves and the soft scrape of shells against sand. Both versions fit the bones we have found. Neither can be proven. The colors, too, are a kind of guess. We see the shapes of the armored swimmers in stone. We rebuild them with care, but the exact shades of their shells, the patterns on their backs, the way light played across their living skin, these have all dissolved into deep time. What we hold in our hands are outlines, beautiful and incomplete, float there a while longer, above the pale mounds and the gliding trilobites. Let the warm, shallow water hold you. This is one face of Earth before the dinosaurs, and it is only one face among many still to come. Imagine an ocean 480 million years old. The light comes down in soft green columns through the surface. Below, the water turns slowly darker, slowly cooler, until it reaches a place where almost no light can follow. Here, drifting near the muddy floor, swim some of the strangest creatures the planet has ever made. They have no jaws. They have no true bones. And yet, in their quiet way, they are the deep ancestors of every fish, every frog, every bird, and every person who would ever live. These were the first vertebrates with any real swimming power. We call them, as a loose group, the Jawless fish. Their mouths were simple round openings, sometimes ringed with small tooth-like plates made of the same hard material as our own teeth. Their bodies were often armored in thick, bony shields across the head and shoulders, while the tail behind stayed soft and flexible. They looked in many ways like little swimming helmets with whips for tails. Some of them rested on the sea floor, sifting through the soft sediment for tiny bits of food. Others rose into the open water, beating their tails against the current. None of them could bite. They sucked. They scraped. They strained. jaws, the whole hunting strategy of the ocean was different, slower, gentler, more patient. A predator could not lunge and snap. It could only draw food in, like a careful straw pulled across the dark. The shapes of these animals still puzzle the people who study them. One kind had a flat, shovel-shaped head and small eyes set close together on top, as if it spent its life looking up. Another had eyes on the sides, with a long, narrow snout. A third had a body covered in tiny diamond-shaped scales, smooth as polished stone. The fossils show such variety in such small windows of time that researchers still debate how all these forms relate to one another. One theory groups them by the patterns of their head shields. Another arranges them by the shape of the inner ear, hidden deep inside the bone. The two family trees do not always agree. Even more mysterious is the question of where these creatures came from in the first place. The earliest fish-like fossils are tiny, fragile things, easily lost to time. By the time the armored, jawless fish appear in numbers, they are already varied, already specialized, already spread across many seas. The long beginning of their story is mostly missing. Some researchers think their ancestors lived in shallow lagoons, where soft bodies rarely fossilize. Others suspect they began in fresh water, in rivers and streams whose sediments have long since washed away. The truth lies somewhere in those lost waters, and we may never recover it. Their world below the waves was not silent. The deep currents carried the soft clicks of shrimp-like creatures and the slow grinding of trilobites on the floor. Great sea scorpions, some longer than a grown person, prowled the shallower reefs. The armored fish kept to the muddy bottoms and the quiet edges, perhaps for safety. Their bony plates were not just decoration. They were defense. Something out there in the dim water was worth hiding from. And yet, slowly, across millions of years, these jawless creatures began to change. Inside the soft tissue at the back of the throat, certain bones that supported the gills began to drift, to thicken, to hinge. Nobody saw it happen. It took ages. But somewhere in this long, quiet experiment, the first jaw appeared. It was perhaps the most important small invention in the history of animal life. With a jaw, a fish could grasp Adhere, chew, defend, choose. The whole future of vertebrates pivoted on that hinge. The jawless fish did not vanish when their jawed cousins rose. A few lineages still swim in our oceans and rivers today, in the form of lampreys and hagfish, soft, eel-like, eyeless, or nearly so. They are not exactly the same as their ancient relatives, but they carry an echo of that older design. When biologists study them, they are reading a faint signal from a world before teeth, before bite, before the long arms race of predator and prey took its modern shape. What remains unknown is just how much of the ocean these early fish truly filled. The fossil record gives us snapshots, not movies. Whole groups may have lived and died without leaving a single trace in stone. The depths of those ancient seas are, in a real sense, still dark to us. We see only the armored ones, the lucky ones, the ones who happened to settle into mud that turned to rock. The rest swim on only in imagination, in the soft green light of a sea that is long gone. For most of Earth's long story, the land was bare. Imagine standing on a continent 470 million years ago. The rocks are gray and orange. The wind carries dust, not pollen. There is no rustle of leaves, no hush of grass, no soft green carpet underfoot. The shorelines are damp and slick with mats of bacteria and algae, but the dry interior stretches for miles in silence. The sky is wide and pale. The sun beats down on stone. Life is busy in the oceans, but the land is still waiting. Then, in slow pulses, something begins to change. Small green smudges appear near the water. They are not yet trees. They are not yet ferns. They are tiny, low things, closer to mosses and liverworts, hugging the wet edges of streams and lagoons. These first land plants had no true roots. They had no veins inside them to carry water. They simply soaked up moisture like sponges and stayed close to the shore. For tens of millions of years, that was enough. The rhythm of plant life on land seems to move in long, patient waves. Each wave reaches a little further inland. Each wave brings a new tool. First came the simple green mats. Then came small upright stems, no taller than your finger, with little knobs at the top that released spores into the wind. These tiny pioneers belonged to a group we now call early vascular plants. Their inner tubes carried water up from the ground. With that one quiet invention, plants could finally stand. They could lift themselves toward the sun. The cycle continued. Stems grew taller. Spores traveled farther. By the middle of the Devonian period, about 390 million years ago, low green thickets covered the wet lowlands. By the late Devonian, some plants had grown into the first true trees. Their woody trunks reached the height of a small house. Their roots pressed down into the soil, breaking rock into grit, drawing minerals upward, locking carbon into their tissues. The land was no longer bare. The land was breathing. How exactly did this happen? On that point, the story grows softer at the edges. One idea is that plants crawled out of the water gradually, in small steps, as freshwater algae adapted to brief dry spells along muddy banks. Each generation tolerated a little more sun, a little less moisture. Over millions of years, that slow adjustment became a full move onto land. Another idea suggests the change was helped by tiny fungi. Some researchers wonder if early plants and ancient fungi formed a partnership in the soil, with the fungi gathering minerals from rock and the plants offering sugars in return. If true, the green takeover of land may not have been a solo act. It may have been a quiet alliance. The evidence is patchy. Fossil spores from this age are common, but full plant bodies are rare. A spore is tough and travels far. A soft green stem rots quickly. So we see the dust of these early forests more often than the forests themselves. The question of which plant came first and where remains open. What is clearer is the rhythm that followed. Plants pulled carbon dioxide out of the air and locked it into wood and soil. As the green spread inland, the atmosphere shifted. Oxygen levels rose. Carbon dioxide levels fell. Some scientists think this slow drawdown of carbon may have cooled the planet, perhaps even helping to trigger glaciations later in the Devonian. Other researchers suspect the cooling came from different causes, like changes in ocean circulation or volcanic quiet spells. The truth likely lies in some braided combination, but the proportions are still debated. There is something gentle in picturing these first forests. They were not loud. They had no birds in them. They had no flowers. Insects were just beginning to explore the new green corridors. The wind would have moved through stiff, simple branches with a dry whisper. Rain would have fallen on bare soil and on the spongy mats below, soaking down into roots that were still learning what roots could do. The cycle of leaf decay and soil was still being invented. Every season was a small experiment. And so the land, once dust and stone, slowly became a living skin. The pulse of plant life set rhythms that the planet still follows. Carbon in, carbon out. Water up, water down. Spring growth, autumn fall. These rhythms began in those quiet early ages, long before any large animal ever walked beneath a canopy. The forests that would one day shade the dinosaurs were rooted, in a way, in these patient first steps. The exact order of those steps is still being pieced together. The first plants on land did not climb mountains. They did not push deep into the dry interior. They began at the edges, where the salt water met the soft mud, where rivers spilled out into shallow lagoons. The coastline was the nursery. It was a thin green ribbon, no wider than a person could walk in an hour, hugging the rim of every continent. From above, an ancient Earth would have looked almost bald, with a faint fringe of color tracing each shore. This thin band of life did not exist alone. It shared its world with strange neighbors on either side. To the seaward side, the shallow water still teemed with armored fish, drifting jellies, and the slow, patient mats of algae. To the landward side stretched a quiet emptiness of bare rock, sand, and dust. The plants stood between two worlds, holding the soft border between them. They were the first true coast dwellers, and they changed both sides of the line at once. On the seaward side, the early plants slowed the water. Their small stems caught silt and broken shells, mud that had once washed straight out to sea now settled at their feet. Over many lifetimes, this trapped mud built up into low banks and gentle deltas. The shoreline itself began to grow outward, claiming a few inches of new ground each century. Some researchers wonder if the green ribbon and the moving mud worked together as a single living system each one shaping the other. Others think the plants were mostly passengers, lucky to grow in places the rivers were already building. The full balance between life and sediment in those early shores is still being worked out. On the landward side, the plants changed the air just above the ground. Their leaves, even the tiny scale-like leaves of the earliest kinds, released slow puffs of water vapor. This small breath cooled the soil and held a thin film of dampness near the surface. Where one plant grew, another could follow. Mosses and liverworts crept inland in patches, finding the moist hollows between stones. Whether they pushed inland on their own or only spread when the climate happened to grow wetter remains an open question. The fossils are too patchy to tell the full story. The animals followed soon after, though we do not know exactly when or in what order. Tiny mites and the ancestors of millipedes scuttled through the damp green mats, feeding on dead plant bits and on each other. Small worms tunneled in the soft soil that the roots were just beginning to build. The first land soil itself is a kind of mystery. It was unlike the rich, dark earth we know today. It was thinner, paler, made mostly of crushed rock and a small amount of plant matter. Some researchers think this early soil was almost as much a creature as the things living in it, since it could not exist without them, and they could not exist without it. The coastlines were also crossing places. River mouths brought fresh water out to meet the salt. Tides brought salt water inland with each high water. Creatures that could survive in both kinds of water had a special advantage here. Some early fish learned to handle the shifting salt levels of the river mouths. Some early plants learned to tolerate brief floods of brackish water. The edge of the sea was a testing ground where the rules kept changing twice a day. Storms were the other great neighbor. Without large inland forests to break the wind, storms swept in from the open ocean and raked the low coasts. Whole patches of green might be torn away in a single afternoon and washed back out to sea. The dead plants drifted, sank, and settled into the seabed mud, where some of them slowly turned to stone. Many of the oldest plant fossils we have were not preserved on land at all. They were buried at sea, swept there by the very storms that killed them. This is one reason the early land record is so quiet. The land kept eating its own evidence, while the sea kept a few pages of the story safe. Standing on one of those ancient beaches, a visitor would have heard almost nothing. No bird calls, no insect hum, only the wind, the soft rush of waves, and perhaps the faint crackle of drying mud. The coastline was busy in its own slow way, but it was a silence that built worlds. From this narrow green seam, life would eventually spread far inland and rise into the air and grow tall. For now, in this chapter of the story, it was content to stay close to the water and wait. Long before any dinosaur left its print in the mud, the land was learning how to grow tall. The first true forests rose during the Devonian period, more than 380 million years ago. To stand among them, if such a thing were possible, would be to stand in a world both familiar and deeply strange. The light would filter through leaves you almost recognize. The trunks would rise into shapes no living forest can quite match. The earliest of these tall plants was a tree called Archaeopteryx. It grew slender and graceful, with feathery branches that fanned outward like soft green plumes. Its trunk could reach more than 90 feet, taller than many modern oaks. Its roots spread wide and deep into the soil, holding the ground together in ways no plant had managed before. For tens of millions of years, Archaeopteryx was the dominant tree on Earth, blanketing the floodplains and river valleys of a young, warm world. Yet stranger still were its neighbors. Among them grew prototaxites, one of the most puzzling organisms ever found in the rock record. Some specimens stood over 20 feet tall, with smooth, tapering trunks as thick as a person's body. For a long time, scientists thought prototaxites was a primitive tree. Others wondered if it might be a giant alga washed inland by some ancient tide. The leading idea today is that prototaxites was a fungus, a colossal living tower of fungal tissue, rising above the low green plants like a pale stone pillar. The competing view holds that it may have been something else entirely, a kind of life that has no close relative alive today. The matter remains genuinely open. Imagine walking through that early forest, The ground would be soft with moss and liverwort, low and damp and quiet. The trees would rise around you in slender columns. And then, here and there, these strange fungal towers would stand among them, smooth and silent, taller than a 2-story house. No birds would sing. No insects would hum overhead in any great number. The only sounds would be wind, water, and the slow creak of wood that had only recently learned how to be wood. The scale of these early forests grew over time. By the late Devonian and into the Carboniferous, the trees climbed higher still. Like apsids, the scale trees reached heights of over 100 feet, with trunks marked in diamond patterns where their leaves had once attached. Calamites, giant relatives of the small horsetail plant you might find by a stream today, grew as tall as a 5-story building. Their hollow, segmented stems swayed in warm, wet winds. Whole landscapes lay covered in these strange green spires, packed close together along the edges of vast inland swamps. The roots of these forests changed the planet in ways that are still debated. As trees grew taller and reached deeper, they pulled minerals from the rock and locked carbon into wood and soil. Some researchers believe this great pulse of plant growth drew so much carbon dioxide out of the air that it cooled the climate dramatically. Others argue that the cooling came from many causes at once, with the forests playing only one part among several. The exact weight of each cause is still being studied. What we do know is that the air itself began to shift. Oxygen levels climbed higher than at any other time in Earth's history. Some estimates place the oxygen content at over 30% of the atmosphere, compared with about 21% today. The reason is thought to be partly the forests themselves, breathing out oxygen on an enormous scale, and partly the slow burial of all that dead plant matter in waterlogged ground, where it could not rot and pull oxygen back out of the air. How high the oxygen truly rose and how long it stayed there are questions still being refined by new measurements in old rocks. The fossils of these forests can be found today in coal seams and stone quarries across the world. Sometimes a single slab of shale will show the perfect imprint of a leaf that fell 300 million years ago. Sometimes, a whole upright trunk is preserved, rooted in the very soil it once grew in, fossilized in place by a sudden flood. These quiet relics are all we have. We will never hear the wind in those branches. We will never smell the damp resin of those bark patterns. What it felt like to stand in such a forest, beneath those soft green fans and those silent fungal towers, we can only imagine. The picture is still being drawn, one fossil at a time, from a world that was tall and strange long before any giant ever walked. Picture a forest floor in the Carboniferous period, around 300 million years ago. The air is warm and thick with moisture. Tall tree ferns sway gently. Sunlight filters down through leaves the size of dinner plates. And then, sliding softly across a fallen log, comes a creature that would make any modern hiker stop in wonder. It is a millipede, but this millipede is as long as a small car. Scientists call it Arthropleura, from the fossil tracks it left behind, and from the rare pieces of its armored body preserved in stone. We can tell it grew up to about 2.5 meters long. That is taller than most people. It moved on dozens of legs, its segmented shell glinting a dull brown red as it slid through the leaf litter. It probably ate plants, though we are not entirely sure. No one alive has ever seen a creature like it, and it was not alone. The skies of this lost world held dragonflies with wingspans wider than a hawk's. The most famous of these, Meganeura, had wings that stretched about 70 centimeters from tip to tip. Imagine the soft, papery sound of those wings beating slowly through humid air. Imagine the shimmer of veined membranes catching the green light. There were giant scorpions too, and spiders larger than any that crawl today, and cockroach-like creatures the length of your forearm. Why were these animals so large? This is the quiet puzzle that scientists have been turning over for more than a century. And the leading idea, though still debated, has to do with the air itself. During the Carboniferous, the great coal forests were pulling carbon dioxide out of the atmosphere and locking it into wood and peat. As they did this, they released oxygen. The best estimates suggest that oxygen levels rose to around 35% of the air, compared to about 21% today. is a remarkable difference. The air would have felt richer, denser, more electric in some hard-to-describe way. Insects do not breathe with lungs. They breathe through tiny tubes called tracheae, which carry air directly into their tissues. In modern insects, these tubes set a hard limit on body size. Beyond a certain point, oxygen cannot diffuse deeply enough to keep a large body alive. But in an oxygen-rich world, that limit shifts upward. More oxygen means insects can grow bigger before their breathing system fails them. One theory says this is why giants ruled the Carboniferous era. The theory is elegant. It fits the timing. The giants appear when oxygen rises and vanish when oxygen falls. Yet some researchers wonder if oxygen alone is the whole story. Other ideas have been proposed. Some scientists point out that in the Carboniferous, there were no birds yet, and no flying reptiles. The skies were empty of fast-moving predators. A giant dragonfly had nothing to fear from above. Under that pressure-free sky, perhaps insects simply had room to grow large without being picked off in flight. Others suggest the climate itself mattered. The warm, wet, stable conditions of these coal forests may have favored slow-growing bodies that simply kept getting bigger across generations. And a few researchers have asked whether the higher oxygen might have actually been dangerous, since oxygen is also toxic at high levels, and growing larger may have been one way for insect larvae to dilute the chemical stress in their tissues. So the giant size might have been a survival strategy, not a luxury. We do not know which of these ideas is closest to the truth. Probably it was some mixture of them. The fossil record cannot tell us exactly how Meganeura behaved, or what Arthropleura ate for breakfast, or how it felt to stand inside a forest where the loudest sound might have been the slow scrape of a millipede, the length of a sofa. The small details of these creatures are themselves a kind of poem. Under a microscope, fossilized fragments of giant insect wing show the same delicate vein patterns we see in modern dragonflies, only scaled up many times over. The compound eyes of Meganeura would have held tens of thousands of tiny lenses, each one catching a sliver of green forest light. Arthropleura's footprints preserved in ancient sandstone, show the rhythmic press of dozens of legs moving in perfect waves, like ripples on water. These were not monsters. They were quiet giants in a quiet world, breathing the rich air of a planet that no longer exists. When the oxygen dropped and the forests changed, they faded away, leaving only their soft imprints behind. Whether they could ever return in some far future where the air shifts again is for most of human history, no one knew that the black rock burning in their hearths was once a forest. People in many parts of the world had found coal seams in cliffs and riverbanks. They knew it burned hotter than wood. They knew it came from deep in the ground. But they did not know that each lump of coal was the squeezed remains of trees that had lived hundreds of millions of years ago in swamps that no human eye ever saw. The first hints came slowly. In the 17th century, a few sharp-eyed observers in England and Germany noticed something strange. When they split open pieces of coal, they sometimes saw the faint shapes of leaves pressed into the black surface. Some saw the bark patterns of ancient trees. Others found tiny stems and seed-like prints. These were not random marks. They looked too much like living plants to be anything else. For a long time, no one was sure what to make of these prints. Some thought they were curious tricks of nature, shapes that grew inside the rock on their own. Others suspected they were real plants, somehow turned to stone. The idea was hard to accept. If coal was made of plants, then the world must once have been very different. Tropical swamps would have to have stretched across places that now held cold farmland and gray cities. In the late 18th and early 19th centuries, geologists began to study coal seams with more care. They walked into mines with lanterns and notebooks. They mapped the layers of rock above and below the coal. They noticed that coal almost always sat between beds of shale and sandstone, and that these layers held fossils of swampy plants. Giant tree trunks sometimes stood upright through several layers, as if the swamp had been buried in place. The pieces began to fit together. A British geologist named William Caniber and his colleague William Phillips gave a name to the long age when these swamps grew. They called it the Carboniferous, which simply means coal-bearing. The name stuck. Across Europe, North America, and later other continents, scientists found the same patterns. Thick coal seams, strange fossil leaves, bark with diamond and scale patterns unlike any tree alive today. The world of the Carboniferous slowly came into focus, even though no one had ever seen it. The picture they pieced together was a strange one. Vast lowland swamps, warm and humid, with standing water for as far as the eye could see. Towering trees with soft, spongy trunks. Ferns the size of houses. Thick mats of dead plant material falling into still water year after year, century after century. Without enough oxygen in the muddy water, the dead plants did not fully rot. They piled up. They were buried. Over millions of years, heat and pressure pressed them into peat, then into coal. There were mistakes along the way. Early naturalists sometimes thought the giant scalebark trees were close cousins of modern palms or conifers. They were not. Those trees, called lycopsids, were tall relatives of the small club mosses that creep along forest floors today. Some early researchers also believed coal had formed quickly in a single great flood. Careful mapping of the many separate coal layers, each with its own fossil soil beneath it, showed that the swamps had grown and drowned and grown again over a stretch of time hard for the human mind to hold. Minds themselves became unintentional museums. Coal miners brought up fossils by the wagon load, often without realizing it. Tree trunks turned to stone. Imprints of dragonfly wings as wide as dinner plates. Sometimes whole fern fronds, dark and delicate, pressed between layers of shale. Museums in cities like London, Pittsburgh, and Essen filled their cases with these treasures. The Carboniferous world, once invisible, began to live again on dusty shelves. Even now, the story has open edges. Researchers still wonder why coal formed so thickly in this particular age, and not as often before or after. One idea is that the ancient trees made a tough material called lignin that fungi had not yet learned to break down, so the wood piled up untouched. Another view suggests that the climate and the shape of the continents mattered more. creating huge low basins where swamp water could not drain. Both ideas may hold part of the truth, and the debate continues in quiet journals and conferences. So when you hear of coal, think of it as a long letter from a vanished world. Each black seam is a buried forest. Each lump in a fire is a piece of a swamp older than any creature with bones on land. The people who first read this letter were patient, careful, and often wrong, until slowly they were right. Somewhere on a quiet shore, more than 350 million years ago, something pressed its weight into wet mud. The mud held the shape. Then more mud washed over it, and more, and the print was buried and pressed into stone. Today, in places like Poland and Ireland and parts of Canada, scientists find these old prints in slabs of rock. They look like the footprints of small four-legged animals. They are some of the strangest fossils we have ever found because they seem to be too old. For a long time, the story of how life walked onto land followed a tidy order. First came fish with strong fins. Then came fish that could push themselves through shallow water. Then came creatures with true legs and toes, walking the soft edges of ancient swamps. That last step, scientists thought, happened around 370 million years ago. But in the year 2010, researchers in a quarry in Poland announced something that did not fit. They had found trackways in rock that was almost 18 million years older than the oldest known walking animal. The prints showed clear toes. They showed an alternating step. They showed something with 4 limbs moving across a tidal flat long before such a creature was supposed to exist. This is the kind of discovery that makes the long story of Earth feel suddenly loose at the edges. If the tracks are real, and most researchers agree they are, then the first walkers came onto land far earlier than the fossil bones suggest. But no bones from that age have been found yet. The bodies that made these prints are still missing. So we have the footsteps without the feet, the journey without the traveler. One idea is that the bone fossils are simply harder to find. Bodies fall apart, soft tissues rot, bones scatter and dissolve. Footprints, oddly, can last longer because they are an impression in mud that hardens into stone. By this thinking, the walkers were there all along, in shallow lagoons and muddy estuaries, and we just have not dug up their skeletons yet. Another idea is that the prints were made by something we would not quite call a true four-legged animal. Perhaps a fish with very strong fins, propping itself along the bottom, leaving marks that look like footprints, but were made underwater. Some researchers find this idea compelling. Others find it hard to square with the clean toe impressions in the Polish slabs. The question is not settled. What is strange when you sit with it is how patient these clues are. A footprint in soft mud should vanish within hours. A tide should erase it. A rainstorm should smear it. For a print to survive into the deep future, a delicate sequence has to happen. The mud must be just damp enough to hold the shape. A gentle layer of sediment must drift in soon after, covering the print without crushing it. Then time must do its slow work, pressing layer upon layer, turning soft mud into rock. Almost no footprint is lucky enough to make it through. The ones we find are the rare winners of a long, quiet lottery. There are other surprises in these old trackways. Some of them show animals moving in groups. Some show prints with no drag mark in between, meaning the bodies were held up off the ground, not slumped like a fish. Some show what look like resting places, where an animal sat down for a while in the mud. These small details bring the scene to life in a way bones never quite can. We get not just the shape of a creature, but a glimpse of its behavior, its weight, its rhythm of movement. Even so, the deeper question stays open. We do not know exactly when life first stepped from water onto land. We do not know whether it happened once or many times in many different places, with many different kinds of bodies trying the experiment. The Polish tracks suggest the timeline is older than we thought. Other prints from other countries hint at still more variety. Yet the bones we would need to be certain remain hidden, somewhere in layers we have not yet split open. So we are left with the image, a wide, shallow coast under a pale sky, warm, shallow water lapping at flats of soft gray mud, and something stepping out slowly, leaving four prints behind, pausing, stepping again. The creature itself is gone, shoreline is gone. The sea that held it has long since drained and reformed elsewhere. Only the prints remain, pressed into stone, waiting for someone to find them and wonder who had walked there, and why, and how long ago. Picture a shallow swamp in the late Devonian, around 370 million years ago. The water is warm and stained the color of weak tea. Tall plants stand in the shallows, their roots tangled in soft black mud. The air hums with the wing beats of early insects, and the sun filters down through fronds the size of dinner tables. In the still pools between the roots, something moves. It is not quite a fish. It is not quite anything we have a clean name for. It has gills, but it also has lungs. It has fins, but inside those fins are bones that look strangely familiar. These were the in-between creatures, the bridges, for a long stretch of deep time. The line between water animal and land animal blurred, and the planet itself seemed to be running an experiment in how a body could be built. The most famous of these strange creatures is known from fossils found in the high Arctic, in rocks that were once a warm river delta. Its body was flat. Its eyes sat on top of its head like a crocodile's, and its front fins ended in small wrist-like joints. It could push itself up. It could probably gulp air. Whether it crawled onto the bank or only lifted its head above the water remains an open question. This is where the symphony of the early world begins to play in full. The shift from water to land was not one creature's quiet decision. It was the result of many systems moving together. The forests we wondered about earlier were now pumping oxygen into the air at levels never seen before. That extra oxygen made it possible for a soft, lung-breathing animal to survive outside the water for longer stretches. The trees also dropped leaves and wood into the swamps, which fed the mud, which fed the plants again, which fed the air. Every breath these early walkers took had been made by a fern somewhere upstream. The sun played its part as well. Long, warm seasons in the equatorial swamps kept the shallows full of slow, oxygen-poor water. In water like that, gills alone are not enough. A fish that could gulp a mouthful of air at the surface had an advantage. Some researchers think this is the deeper reason lungs appeared at all. Lungs may not have evolved to leave the water. They may have evolved to survive in it. The walk onto land in this view was a side effect of a much older trick. There are other theories. Some scientists wonder whether the first walking limbs were shaped less by the need to breathe and more by the need to hide. A shallow swamp full of larger predators is a dangerous place for a soft creature. Being able to push yourself into the reeds or wedge yourself under a log or lift your eyes above the waterline to watch for danger may have been the real prize. The bones that would one day become our wrists and ankles may have started as tools for crouching in mud. We do not know for sure which pressure pushed hardest. Weather, too, joins the chorus. The Devonian climate swung between wet and dry. Rivers rose and fell. Pools that were deep one month became puddles the next. A creature that could heave itself across a drying mudflat to reach the next pool would live. One that could not would dry out under the sun. Across thousands of generations, the ones who could shuffle, lift, and gulp passed on those gifts. The land did not invite life. The shrinking water pushed it, and the chemistry of the planet was listening. Carbon dioxide was being pulled from the air by those vast new forests and locked away in peat and stone. The climate cooled in long, slow steps. The oceans shifted. Reefs that had ruled the warm seas began to falter. A great extinction, still poorly understood, swept through the seas late in the Devonian, thinning out the armored fish and many of the old reef builders. The in-between creatures, half in the water and half out, slipped through that narrow door. The land had less competition now. The shore was open. What we are watching across all of this is a planet behaving like a single connected instrument. The plants make the air. The air makes the animals possible. The climate sets the stage. The extinctions clear the floor. No single piece moves on its own. The question that lingers, soft as the warm Devonian rain, is which note led the music. Was it the lungs, the limbs, the swamps, the oxygen, the drying pools, or some quieter thing we have not yet learned to hear? The mud has not finished telling us. Somewhere in the long, warm middle middle of the Carboniferous, in a swamp we will never see, something small was changing. The change was so quiet that no one watching at the time would have noticed. A small four-legged creature, perhaps no bigger than a lizard, laid an egg on dry ground. The egg had a tough, leathery shell. Inside, the tiny life within carried its own private pond. This was the beginning of the reptiles, and it was the beginning of a new way of being alive on Earth. For tens of millions of years, the amphibians had ruled the wet places. They needed water. Their soft jelly eggs had to be laid in ponds or damp mud, or they would dry out and die. The young hatched as swimmers, breathing through gills, and only slowly grew into air-breathing adults. Life, for them, was always tied to the shoreline. The first reptiles broke that tie. Their eggs carried a small folded membrane called the amnion, a thin sac of fluid that cradled the growing young. The shell kept water in. The shell kept the world out. With this single invention, the inland deserts and dry uplands became reachable. A whole continent of empty space opened up. We call these early creatures amniotes, the egg with a membrane animals. Every reptile, every bird, every mammal alive today, including the listener drifting toward sleep, descends from that quiet lineage. We carry the memory of that first dry land egg inside our own beginnings. The oldest known amniote fossils come from rocks in Nova Scotia, in Canada, inside the hollow stumps of ancient lycopod trees. A small creature called Hylonomus was found curled in the rotten wood, about 312 million years old. It had a slim body, small, sharp teeth, and long, delicate toes. It looked, in its own quiet way, a little like a modern lizard. But it was not a lizard. It was something older, something closer to the root of the family tree, before the great branches had grown apart. How exactly the amniotic egg evolved is one of those questions that may never be answered. Eggs do not fossilize well. The soft membranes leave almost no trace. Researchers can study living amphibians and living reptiles and infer the steps in between. But the actual moment, the actual creature that first laid such an egg, is hidden from us. One idea is that the change happened slowly, over many generations, with eggs becoming gradually tougher and drier. Another idea is that some early amniotes may have given live birth first, and the hard-shelled egg came later. The evidence is incomplete. The fossils are silent on this point. What we do know is that once the amniotes appeared, they split quickly into two great lines. One line led toward the reptiles and birds we know today. The other line led toward the mammals, including, eventually, us. The split happened deep in the Carboniferous, in the shadow of those giant coal forests, while dragonflies the size of crows still hummed over the water. The early reptiles were small and quick. They scurried under fallen logs and through dry leaf litter. They ate insects and perhaps each other. They could go places the big amphibians could not. They could climb. They could wait out the dry season. They could lay their eggs in a hidden dry place and walk away. That small freedom, that small independence from the water, would carry their descendants across the whole world. The land they spread into was changing too. The vast, wet swamps that had built the coal beds were beginning to dry. The climate was shifting. Higher, drier ground was becoming more common. The amphibians, tied to their ponds, found their world shrinking. The reptiles, tied to nothing but their own leathery eggs, found their world growing. It is easy to imagine that this transition was a sudden victory. It was not. It took tens of millions of years. The amphibians did not vanish. They are still here in the frogs and salamanders that sing in our spring nights. But the balance of power on land had begun to tilt very slowly toward the dry-skinned, dry-egged newcomers. What strikes the patient observer is how small the change seemed at the time. A slightly tougher egg, a slightly drier skin, a slightly more efficient lung. None of it looked like the beginning of an empire. And yet, from that quiet shift in the swamp would come the dinosaurs, the birds, the mammals, the entire furred and feathered and scaled world that fills the earth today. The vast future was hiding inside a small leathery shell, on a dry patch of mud, in a forest that no longer exists. The Permian sun rose over a world that no longer belonged only to the swamps. The great coal forests had begun to thin. In their place, drier plains stretched out beneath a brighter sky. And and across those plains walked some of the strangest animals Earth has ever produced, long-bodied creatures with tall sails of skin rising from their backs like ship masts made of bone. These were the sail-backed wanderers. Their proper name is pelycosaurs, a group that included animals like Dimetrodon and Edaphosaurus. They were not dinosaurs. They lived long before dinosaurs walked the planet. They belonged to an older branch of the family tree, one that would eventually lead by a very long road to mammals. But in their own time, they were the lords of the land. What made them so unusual was that sail. Tall spines grew up from their spine bones, and skin stretched between them, holding blood and warmth and light. When the morning sun touched that sail, it must have glowed. Imagine the soft pink of early dawn shining through thin skin, the dark shadow of bone stretched across it like the ribs of a paper lantern. A sail-backed animal standing sideways to the rising sun would have looked, for a moment, almost like a piece of stained glass moving slowly across the plain. Why did the sail exist at all? This is one of the gentle mysteries of the Permian, and the question has never been fully settled. One long-standing idea is that the sail helped the animal control its body heat. In the cool morning, it could turn sideways to the sun, catch the warm light, and heat its blood quickly. In the hot afternoon, it could turn into the wind, letting the breeze cool the same blood as it passed through the thin web of skin. A creature with a sail could be ready to hunt, while other animals were still slow and stiff with the night chill. A second idea is that the sail had little to do with heat at all. Some researchers wonder if it was mostly for display. A bright sail, perhaps streaked with color, could have helped these animals find one another across the open ground. It could have warned off rivals or attracted mates. We see this kind of showy structure in many living animals today, from peacock tails to the throat fans of certain lizards. Perhaps the Permian plains were dotted with sails flashing red and gold in the long light of evening, each one a quiet message sent across the dust. A third possibility is that the sail did several things at once: heat control, display, even camouflage among tall reeds. The truth may be a blend of all these ideas. The fossils themselves cannot tell us the color of the skin or the patterns it carried. That part of the picture is gone. We are left to imagine. The light of the Permian was different from the light of the swamp ages before it. The thick mists of the coal forests had lifted in many places. The air was clearer. The sky in some regions was a hard, bright blue, with high clouds scattered like white feathers. Shadows fell sharp and long across red soils and pale stone. A sail-backed predator stalking through that light would have cast a strange, fluted shadow, the shape of its sail printed onto the ground beside it. Dimetrodon, the most famous of these animals, had teeth of different shapes in its jaw. Sharp ones in front, more knife-like teeth along the side. This was a new pattern in the history of land animals. Most reptiles of the time had simple rows of similar teeth. Dimetrodon was already showing a hint of the dental variety that mammals would later carry. In that mouth, in those teeth, we can almost see the long, slow road towards something like us. Other sail-bearers were not hunters at all. Edaphosaurus, with its smaller head and blunt teeth, seems to have eaten plants. Two creatures with the same body plan, the same towering sail, living very different lives. Why both groups settled on the sail remains an open question, and that shared shape is part of the puzzle. We will never see the sail-backed wanderers in life. We can only stand at the edge of their world in imagination, watching the morning light pour over a red plain, watching the slow procession of strange shapes catching the warmth of a Permian sun. Whether those sails were heaters, banners, or both, they belong to a chapter of Earth's story that ended long before the dinosaurs began. Their light still reaches us, faintly, through stone. Close your eyes for a moment and try to imagine the sound of a single continent. Not many continents drifting on their own currents, the way our world is shaped today, but one enormous landmass holding nearly all the dry ground on Earth. The land would have hummed with its own slow voice. Wind would have crossed thousands of miles of unbroken interior without ever finding the cool relief of a sea. Storms born in one corner could roll for weeks before fading. This was Pangaea. The name comes from Old Greek words meaning all lands. around 250 million years ago, the slow drift of tectonic plates, the great slabs of rock that carry the continents, gathered nearly every piece of land into one shape. From space, it would have looked like a vast pale crescent curled against a single world-spanning ocean called Panthalassa, which means all seas. The sound of such a world is something we can only guess at. Picture the deep interior, far from any coast. The air there would have been dry, almost brittle. Thunderstorms must have been enormous, fed by hot rising air that had nowhere cool to go. Lightning would have cracked across red skies. Some researchers suspect these inland storms were among the most violent in Earth's history, though the evidence comes only from the patterns left in ancient stone. Along the coasts, the sound would have been very different. Waves of a single great ocean swept thousands of miles before breaking on the shore, with no smaller seas to slow them. Swells could grow long and patient and deep. Some scientists wonder whether the surf of Pangaea's coasts had a slower, heavier rhythm than any beach we know today. Others argue the waves were not so different, since wind, not distance, sets most of their shape. The question stays open because we cannot listen to a vanished sea. Inland, there were strange silences too. Vast deserts spread across the heart of the supercontinent. Rain almost never reached them. In places, the only sound would have been wind moving across dunes and the soft creaking of dry plants. No songbirds yet, no mammals calling. The early reptiles and their cousins likely hissed, grunted, and shuffled. But the air did not yet carry the layered music of a modern forest. The land itself made sounds we would recognize. Earthquakes shook the crust as plates ground together along the edges where Pangaea was still forming, and later where it began to crack apart. Volcanoes rumbled in long chains. Near the end of this age, in what is now Siberia, enormous eruptions began that would last for hundreds of thousands of years. The ground there would have groaned and split, releasing gases that drifted across the whole supercontinent. The sound of that slow upheaval is gone, but the basalt it left behind still covers an area larger than many modern countries. Rivers cut long, winding paths across Pangaea. without smaller continents to break the land. Some of these rivers may have been astonishingly long, carrying water from highland interiors all the way to the single ocean. The murmur of such rivers, broken by waterfalls and shallow rapids, would have been one of the gentler voices of that world. Fossils of fish and amphibians in old riverbeds suggest these waters were busy with life, even as the deserts around them stayed mostly still. What we know about Pangaea comes from matching shapes and stones. The eastern coast of South America fits into the western coast of Africa like two pieces of a torn page. Similar fossils appear on continents now separated by oceans, hinting that animals once walked freely between them. Mountain ranges that now end at coastlines seem to pick up again on distant shores. These clues, gathered slowly over more than a century, let us reconstruct the rough outline of the supercontinent. The finer details, the height of its mountains, the temperature of its interior, the colors of its skies, remain partly guesswork. One theory holds that supercontinents like Pangaea form and break apart in long cycles, perhaps every 400 or 500 million years. If that is true, the continents we know today are simply a passing arrangement, drifting toward some future gathering we will never see. Another view suggests these cycles are less regular than they appear, shaped by forces deep in the mantle we do not yet fully understand. Both ideas are still being tested. For tonight, it is enough to picture that one great land, holding its long breath under a single sky. A world whose sounds we can almost hear if we listen quietly enough to the stones that remember. Inside the heart of Pangaea, far from any coast, the land grew strange. The great supercontinent had pulled itself into a single mass, and the middle of that mass became one of the driest places Earth has ever known. To picture it, imagine standing on red sand that stretches without break in every direction. The wind moves in long, slow sheets. There are no trees, no rivers, no soft green edges, only dunes and more dunes, rolling toward a flat brown sky. The numbers behind this dryness are surprisingly simple. Moist air rises off the ocean, cools, and drops its water as rain. But But moisture can only travel so far before it runs out. On a normal continent, the distance from coast to coast is maybe a few thousand kilometers. On Pangaea, that distance could stretch to 10,000 kilometers or more. By the time clouds reached the interior, they had nothing left to give. The math of evaporation and rainfall played out across such a vast slab of land made deserts almost inevitable. There is a quiet elegance in how this works. For every kilometer inland, a small fraction of moisture falls away. Multiply that loss by thousands of kilometers, and the air arrives bone dry. The same simple rule shapes the dry hearts of every large continent today. It shaped Pangaea on a scale we can barely imagine. Geologists read this ancient dryness in the rocks. Across what is now the American Southwest, across parts of Europe, across northern Africa, and into Asia, they find thick layers of red sandstone. The red color comes from iron that has rusted in open air, a chemical signature of long exposure to oxygen without much water to wash it away. Inside the stone, frozen forever, are the curving lines of ancient dunes. The angle of those curves tells the direction of winds that blew more than 250 million years ago. From those wind angles, researchers have tried to reconstruct the weather patterns of the Permian and Triassic. The math is delicate. Wind direction, dune shape, grain size, and the tilt of the bedding layers all feed into models of how air moved across the supercontinent. One picture that emerges is of vast seasonal winds, something like monsoons, but stretched across a continent so wide they may have behaved in ways no modern monsoon can match. Some researchers call these the mega monsoons. Others wonder if the term is too tidy, and if the real climate was far more patchy and strange than any single word can hold. What the math agrees on is the scale. The dry belt of Pangaea was likely the largest desert system Earth has ever seen. It dwarfed the Sahara. It may have covered an area equal to several modern continents put together. Inside it, temperatures swung wildly between day and night, between season and season. Rain, when it came rarely, and sometimes in violent bursts that carved short-lived channels across the sand before vanishing again. Life still found a way in. Tracks preserved in those red rocks show small reptiles moving across the dunes. Some left trails of tiny footprints between scattered scratches, hinting at tails dragging in the sand. Burrows hint at animals sheltering from the heat. How these creatures survived so far from open water remains an open question. One idea is that they followed seasonal flushes of rain, breeding quickly and waiting out the dry months in deep burrows. Another idea is that the deserts were not quite as empty as the rocks suggest, and that small oases of life dotted the interior. In places, the fossil record has not preserved. The mathematics of orbits may have played a quiet role in all this. Earth's tilt and the slow wobble of its axis follow patterns that repeat across tens of thousands of years. These cycles, named for a Serbian researcher who worked them out a century ago, change how sunlight falls across the planet. In some periods, the dry belt may have grown wider. In others, it may have softened, letting green creep in at the edges. The rhythm is regular enough to be predicted, yet its effects on any one place across deep time remain hard to untangle. What lingers in the end is the picture itself. A planet held together as one great land. A red interior so wide that clouds gave up before reaching its center. Wind drawing endless curves into stone, and small, leathery creatures crossing it under a hard sun. The numbers behind that world are simple. The world they describe is something we have never seen and may never see again, and we are still learning how to read it. Around 252 million years ago, at the end of the Permian, the slow rhythm of life on Earth nearly stopped. The fossil record from that time tells a quiet, sobering story. In the rocks just before the boundary, the seas teem with armored fish, coral-like reefs, sponges, and strange shelled creatures. In the rocks just after, almost all of it is gone. Scientists call this event the Great Dying, and it remains the largest known loss of life in the planet's history. The numbers are hard to picture. Some estimates suggest that more than 90% of ocean species vanished. On land, perhaps 70% of vertebrate families disappeared. Even insects, which had ruled the air for tens of millions of years, took a heavy blow. No other extinction has come close to this one. And yet, despite a century of study, the exact cause is still debated. One leading idea points to a vast outpouring of lava in what is now Siberia. The rocks there are called the Siberian traps. They formed when molten material poured from the ground for perhaps 1 million years, covering an area larger than most modern countries. The lava itself was not the killer. The trouble, many researchers believe, came from what the eruptions released into the air. Carbon dioxide, sulfur, methane. The atmosphere thickened with these gases, and the climate began to shift. If this view is correct, the planet warmed quickly. The oceans grew hotter at the surface. Warmer water holds less oxygen, and so the deep seas may have turned still and stagnant. Some sediments from that time show chemical signs of waters with almost no oxygen at all. In such conditions, most ocean life cannot breathe. The reefs went silent. The shellfish vanished from the muddy floors. Even the tiny plankton that fed the whole food web seemed to have collapsed. A competing idea suggests the cause was not the eruptions alone. Some researchers wonder whether the warming triggered a release of frozen methane from the sea floor, which then warmed the planet further in a runaway loop. Others point to falling sea levels, changes in ocean chemistry, or a slow loss of habitat as the supercontinent of Pangaea dried out. Most likely, several of these forces acted together. The question of which mattered most remains open. What makes the Great Dying so striking is how it shows the thinness of the system that holds life in place. Earth sits at a careful distance from the sun, not so close that the oceans boil away, not so far that they freeze solid. The atmosphere is a delicate blanket, only a few dozen miles thick, and within it, the balance of gases shapes everything. A small shift in carbon dioxide, a small change in ocean temperature, a small drop in oxygen, and the web of living things can begin to unravel. In the Permian world, that unraveling happened slowly by human standards, but quickly in the long view of deep time. Perhaps it unfolded over tens of thousands of years, perhaps over a few 100,000. rocks do not always speak in clear numbers. What they do show is layer upon layer of vanished creatures, with simpler, smaller forms taking their place above the boundary line. The land suffered too. Forests that had stood for ages thinned and broke apart. Pollen grains in ancient sediments give way to spores of small, hardy plants, the kind that grow quickly in disturbed ground. Soils washed away without deep roots to hold them. Rivers, freed from the slow grip of plant cover, carved new paths across the drying continents. For a long stretch afterward, the world seems to have grown quieter, dustier, and warmer than before. Sit for a moment with the strangeness of it. A planet that had cradled life for more than 3 billion years came within reach of losing it all. Not from a single blow, but from a long, slow tipping of the scales. The sun still rose. The tides still moved. But the chorus of living voices grew thin. Scientists still wonder what the recovery looked like in the first dark ages after the loss. They wonder how some creatures pulled through when so many did not. They wonder whether the same mix of pressures could ever build again in some far future shaped by forces we cannot yet see. The deep past does not give simple answers. It offers a record, layer by layer, of a world that nearly went silent. And tonight, as you rest, the planet beneath you keeps its quiet balance. Warm enough, cool enough, breathing in its slow and ancient way, while the memory of the great dying waits in the stone below. After the great dying, the world fell into a deep hush. Most of life was gone. The seas held only a thin scatter of survivors. The land lay scorched and quiet under a sky still dim with the dust of catastrophe. And yet, somehow, life did not end. Something held on. Something crept through the ash. The strangest part of this whole story is that we still cannot say, with any certainty, how the survivors survived at all. The fossils from those first thin layers above the extinction boundary are rare and puzzling. In some places, only a single shell species fills the rock for thousands of years. In other places, the layers seem almost empty, as if life had retreated to small hidden pockets we have not yet found. The world after the great dying feels, to the geologists who study it, like a stage with most of the actors missing. Who was left in the wings? Where were they hiding? The honest answer is that we do not fully know. One survivor we keep finding is a small, pig-shaped creature called Lystrosaurus. Its bones turn up across nearly every continent in the early Triassic rock. For a time, it seemed to rule a quiet world almost by itself. Some researchers think Lystrosaurus thrived because it could burrow underground, escaping the worst heat and bad air at the surface. Others wonder if it simply bred quickly, filling empty space left by the lost giants. A third idea suggests it had lungs that worked well in low oxygen air, which may have been common in those bleak centuries. The evidence is still being weighed, and no single theory fully wins. In the oceans, the survivors are even harder to read. A few small clam-like shells, a few coiled ammonoids, a handful of bottom dwellers. That is most of what the rock gives us. Coral reefs, which had built whole underwater cities for ages, vanished almost entirely. For perhaps 10 million years, the seas seem to have held no true reefs at all. Why did it take so long for them to return? One idea is that the water itself stayed too warm, too acid, too low in oxygen for the reef builders to grow. Another idea is that the right species simply had not yet evolved. Both ideas may be partly true. The full picture remains out of reach. There are also fossils so strange that scientists cannot agree on what they even were. Thin mats of microbes spread across the early Triassic seafloor, much as they had in the ancient ages before complex life. Some researchers see this as a sign that the oceans had slipped backward, almost to a younger Earth. Others see it as a sign of stress, a world where simple life thrived because complex life could not. Whether this microbial return lasted years, centuries, or millions of years in different places is still being mapped out. Each new core of rock pulled from the deep adds another small clue. On land, the puzzles deepen. Some plant fossils from the recovery layers show odd, twisted growth, as if the climate kept shifting in ways the plants could not handle. Pollen from ancient ferns appears in waves, with long, quiet gaps between. Some scientists think the climate kept lurching between hot and cool, wet and dry for millions of years after the extinction. Others think the gaps in the pollen record are just gaps in preservation. Which one is closer to the truth may shape how we understand all future recoveries, including the one Earth is in now. There is also the question of why the recovery took so long. After most mass extinctions, life bounces back in a few million years. After the Great Dying, it took perhaps 10 million. Some researchers point to long pulses of volcanic activity that kept stressing the planet. Others point to broken food webs that could not knit themselves back together quickly. The truth may involve both, and other causes we have not yet identified. What lingers in the mind is how much of this story remains hidden in stone we have not yet split open. Every cliff face in Siberia, every desert outcrop in South Africa, every sea cliff in northern Italy might hold one more clue. Somewhere in those layers is the story of how Earth pulled itself back from the edge. The bones and shells and pollen grains are waiting. The patient work of reading them goes on, one tiny fossil at a time. For tonight, it is enough to picture the quiet world that followed the long silence. A burrow in warm earth, a small creature breathing slowly in the dark, a planet not yet ready for giants, but not finished either, holding on, waiting for what would come next. After the Great Dying, the world stayed quiet for a long time. The forests were gone. The reefs were gone. The strange, sail-backed wanderers were gone. What remained was a planet that had to learn how to be alive again. And the most patient teachers in this slow recovery were the plants. The first green to return did not look like a forest. It looked like a thin fuzz on damp ground. Small ferns, low mosses, tough little plants called lycopods, related to the giants that once built the coal swamps, but now reduced to crawling cousins. They spread across the cracked earth in soft mats, holding the soil in place with quiet roots. From the air, the continents of the early Triassic would have looked pale and dusty, with only thin smears of green near rivers and shores. Scientists call this strange interval the coal gap. For nearly 10 million years after the extinction, the rocks hold almost no coal at all. Coal forms from dense, layered plant this gap, the great forests simply were not there to leave it behind. One idea is that the climate had grown too hot and dry for the old swamp giants to come back. Another idea is that the fungi and insects that once broke down dead wood had also collapsed, and the chemistry of the soil itself had to be rebuilt before big forests could rise again. The truth may be a quiet blend of both. The evidence is still being read from the stone. The seas recovered on their own schedule. In the shallow waters, small shelled creatures returned first. Snails, clams, tiny sea lilies waving on slender stalks. The great reef builders of the Permian were gone forever, and the new reefs that slowly grew in their place were built by different architects, made of different minerals, holding different shapes. A coastline that had once shimmered with vast living walls of coral now held only modest patches of shell and stone. It would take tens of millions of years for true reefs to bloom again in their full glory. On land, the survivors began to spread. Small reptiles with sturdy legs moved across the warming plains. Strange beaked creatures, distant relatives of the sail-backed wanderers, browsed on the returning ferns. And among them, almost unnoticed, walked the slender ancestors of the dinosaurs. They were not yet giants. They were lean, quick, and quiet, no larger than a dog, slipping between the ferns on long back legs. The world had room for them now. The throne was empty. This slow return of green carries a question that reaches far into the future. If life can rebuild itself after such a deep wound, what does that mean for the planet 1,000,000 years from now, or 100 million, or 1 billion? The continents are still drifting. Africa is pressing into Europe, slowly closing the Mediterranean. Australia is sliding north toward Asia. The Atlantic is widening by a few centimeters each year, about the speed your fingernails grow. In 250 million years, some models suggest the continents may gather again into a new supercontinent, sometimes called Pangaea Ultima, sometimes called Amasia, depending on which path the drifting plates take. Other models disagree on the shape entirely. The deep future of the map is still an open question. The sun itself is slowly brightening. In about 1 billion years, it will likely be warm enough to boil away much of the surface water, and the green that has covered this world for so long may finally retreat. But that is a story for a planet very different from the one we know. Between now and then lie countless quiet recoveries, countless slow returns of green, countless small creatures that will inherit empty worlds and rebuild them in shapes we cannot picture. What the early Triassic teaches in its dusty, patient way is that the planet does not end when a great age ends. It simply begins again, more slowly than we can imagine, with smaller players and softer footsteps. The ferns came back. The shells came back. The forests eventually came back, though they wore new leaves and new bark and new names. And somewhere in the warming plains, on long, quiet legs, the future was already walking. What kind of planet was Earth in the long ages before the dinosaurs? By this point in the story, it is becoming a planet preparing itself, almost without noticing, for the giants that are about to arrive. The stage is set. The green is returning. The air is steadying. And the small, slender creatures moving through the ferns do not yet know what they will become. In the warm middle of the Triassic, while the air still carried the dust of recovery, a strange company of creatures shared the land. They were not yet dinosaurs. They were something stranger, something older, something that would soon stand in the shadow of the giants to come. Walking the riverbanks were squat, barrel-bodied reptiles with beaked faces and tusks pointing downward, animals called dicynodonts. They cropped low plants with the patience of cattle, and their kind had survived the great dying when so many others had not. Beside them moved the cynodonts, small and quick, with whiskered snouts and teeth that fit together in careful rows. Their bones whispered of a future no one could yet see. From this branch, in the slow turning of millions of years, the first mammals would one day emerge. For now, they were modest creatures, hiding in burrows, watching the world with warm bodies and bright eyes. The rivers held their own caste of cousins. Long-snouted phytosaurs floated like logs in the shallows, looking very much like crocodiles, though they were not. Their nostrils sat high on their skulls, near their eyes, a small detail that tells modern scientists they were something else entirely. On the banks, armored etosaurs lumbered in their bony plating, like living tanks with leaf-shaped teeth, gentle browsers wrapped in fortress skin. And then there were the Roysuckians, tall-legged hunters with deep skulls and curved teeth, walking upright in a way that looked, to our eyes, almost dinosaur-like. For a long time, they ruled the Triassic plains. If you had visited that warm world, you might have thought they were the future. You would have been wrong. Among them, smaller and lighter, ran the earliest true dinosaurs. They were not yet kings. They were quick little things, two-legged, sharp-eyed, sharing the land with all these stranger cousins. For tens of millions of years, they were a minor part of the cast. What changed the story remains an open question. One idea holds that another extinction at the end of the Triassic swept the Roysuckians and many others away and left the dinosaurs with an empty stage. Another view suggests the dinosaurs were already gaining ground through quiet advantages of breathing or growth. The evidence is still being read from the rocks, and researchers continue to wonder. Step back now, far back, until the Triassic shrinks to a thin band in a much longer story. Behind it stretch the Permian deserts, the coal swamps, the first forests, the armored fish, the soft-bodied dreamers of the Ediacaran, the patient mats of stromatolites breathing oxygen into a young sky. Behind those, the dark oceans of a planet still learning what life could be. Behind those, a molten world cooling under a sky thick with steam. And behind that, something stranger still. The atoms in those early seas, the iron in the first fish, the calcium that would one day stiffen the first bones on muddy shores, were forged in the hearts of ancient stars. The carbon in every carboniferous fern, the oxygen exhaled by every cyanobacterium, the phosphorus that built the teeth of the cynodonts and the bones of their distant descendants. All of it came from somewhere older than Earth. The planet did not invent its materials. It inherited them. So when we look at a fossil of a dicynodont, or the print of a fern in a slab of coal, we are looking at starlight that learned to walk, to root, to breathe. We are looking at atoms that drifted for ages before they found themselves arranged into something that could move and eat and rest. The same atoms that warmed in Permian sun now warm in your hand as you lie still. The calcium in your bones is older than the dinosaurs, older than the trilobites, older than Earth itself. This is the widest view. The long silence before the giants was not empty. It was a slow conversation between rock and water and air and light, with life learning a little more in each chapter. The strange cousins of the Triassic were one verse in that conversation. So are we. So is the quiet room around you tonight. What kind of planet was Earth in the long ages before dinosaurs? It was a planet practicing breath, practicing bone, practicing forest and reef and footprint. And it is practicing still in ways we cannot yet read. The deep past holds many open questions, and many of them may stay open for a long time. That is part of their gift. They give us something to wonder about as the night grows quiet and the world turns slowly beneath us. We have come a long way together tonight. We have drifted through quiet ages most of us never learned to name. We have watched the seas darken with the first soft life. We have walked beside reefs of strange armored swimmers and through forests where the tallest trees were not yet trees at all, but towering relatives of the small mosses that today grow between stones. We have listened to the slow breathing of an ocean learning to hold oxygen. We have watched green creep onto bare rock, one tiny patch at a time. We have stood on the muddy shore where something with fins pulled itself up to look around. We have wandered through swamps so thick with plant life that their fallen bodies became the coal still buried beneath our cities today. We have felt the weight of the great dying, the long silence that followed, and the quiet courage of the small creatures who lived through it. We have seen the strange cousins of the dinosaurs rise into a world that was still finding its shape. And through all of it, we have stayed with one open question. What kind of planet was Earth before the giants came? And what does that deep past whisper to us about what is still to come? The honest answer, even now, is that we only know pieces. The rocks keep most of their stories to themselves. Whole ages have left almost no fossils at all. We guess at the colors of ancient skies. We argue about the temperature of ancient seas. We sketch the shapes of continents from clues that are faint and broken. Each new discovery shifts the picture a little, the way wind shifts the surface of a pond. And yet, even in not knowing, there is something gentle. The planet beneath you tonight is the same planet that held those quiet seas, those tall ferns, those soft beginnings. The atoms in your hands have been here through every age we have spoken of. They were in the warm, shallow water where stromatolite mats made the first oxygen. They were in the rain that fell on the first forests. They were in the long Triassic dawn when the world was learning, once again, how to be alive. Picture the Earth now from a quiet distance. A small blue and white world turning slowly in the dark. Its oceans catch the moonlight in soft silver bands. Its clouds drift in lazy spirals over continents that are still, very slowly, moving. Somewhere a desert lies cool under starlight. Somewhere a forest breathes out into the night. Somewhere ice creaks gently on a still lake. Somewhere a wave lifts and falls along an empty shore. This is the same planet that once was a frozen ball of white. The same planet that once was warm from pole to pole. The same planet that lost almost everything and then patiently grew it all back. It has been many worlds inside one world. It will be many more. You are a small part of one of those worlds, a brief, soft, breathing chapter. And tonight, your only task is to rest. The mysteries will still be here in the morning. The fossils will still be locked in their patient stones. The questions will still be open, waiting kindly for whoever wishes to wonder about them next. Let your shoulders soften. Let your breathing slow. Imagine the long, calm turning of the planet beneath you. Imagine the soft hush of an ancient sea, somewhere in the deep past, lapping at a shore that no longer exists. Imagine the quiet green of the first forests, holding the light of a younger sun. Imagine all the small lives that came before yours, each one a tiny flame, each one passing on the warmth. We may learn more about the world before the dinosaurs in the years ahead. New fossils will be found. Old rocks will be read in new ways. Some theories will fade, and others will rise. Some questions we ask tonight will still be open when our grandchildren ask them. That is not a sadness. That is the long, slow, beautiful patience of the earth itself. For tonight, It is enough to have wondered. It is enough to know that beneath your feet lies a planet full of soft secrets. It is enough to feel held by a world that has carried life through ice and fire and silence, and is still here, still turning, still gentle. Rest now. The earth will keep its mysteries safe until you wake. Subscribe for a brand new Earth topic every night. One tap, and something wonderful is waiting for you tomorrow. Sweet dreams.